My name is John Belcher. I'm in the Department of Physics at MIT. I'd like to describe the TEAL program that I'm involved in here. TEAL stands for Technology Enhanced Active Learning. So I'm teaching freshman physics, introductory physics, using a lot of technology in an active learning environment. I'd like to describe what we're doing in both of those aspects, both the technology and the active learning aspect. Let me first say a little bit about my background. I've been at MIT for 30 years. In the early 90s, I taught the large freshman physics course in electromagnetism. Everyone at MIT has to take 2 terms of physics, mechanics, and electromagnetism. So we have large enrollment courses. In particular, the course I taught in the early 90s had 700 students in it. That's normally taught in a passive manner, that is, it's lecture recitation, 3 hours of lecture and 2 hours of recitation. I would do the lectures, and a number of faculty would do recitations. And for a long time, MIT has not had laboratories associated with these large courses. For smaller versions there were, but not for the large course. So for the majority of students, they did not have a physics lab. What TEAL does is a number of things. Most importantly, from a viewpoint of a lot of physics faculty, is we're reintroducing labs in the terms of small desktop experiments that are done in the class period. Let me tell you what a class period is like. Instead of 3 hours of lecture in a large lecture hall and 2 hours of recitation in groups of 30, we have the students come to 5 hours of class in the same room. The room is a studio physics room. It has 13 tables. We put 9 students at a table, and we group the students into subgroups at that table, 3 students in a group. Each group of 3 has a laptop which is networked, and when we do experiments, each group of 3 has an experimental setup to measure the phenomena. For example, they will have an A to D converter that feeds data into the laptop, and for example, a Hall probe to measure the magnetic field of a current carrying coil. So the first thing about this is we're reintroducing experiments back into freshman physics. The second thing about it is it's not passive in the sense of listening to a lecture is passive. The pedagogy is very interactive in these 5 hours that we have them in this classroom, and let me describe a little of that. We will give mini lectures, 10 or 15 minutes of lecture, and that will be broken up by desktop experiments where the students collaborate with each other doing the experiment. Also, we will have students do workshops and problem solving where the students will solve problems as a group of 3, and turn in a common worksheet. We have the students grouped according to ability. That is, we have heterogeneous grouping. We try to put in a group of 3 a range of abilities so that the more prepared students can help the less prepared students. And that's good for both of them. That is a common phrase you hear is, "I never understood this until I taught it." And the idea is to get the better prepared students to explain things to the less well prepared students. It's good for both of them. The less well prepared students, it's obvious. The better prepared students have to formulate the concepts so that they can explain them, which really helps. Any teacher will tell you that is really when you start to understand the fundamentals of the subject, that you really think it through when you have to explain it. So the whole package is much different from passive lectures and recitations. We have them for 5 hours, and we have them work. In addition to many lectures, we have them work in groups collaboratively, both to do experiments and to do problem-solving exercises. The other aspect of this that I really appreciate is the fact that the experiments are done in the context of the mini lectures. If you look at the normal lab setup in many places, you have a lab on Thursday afternoons, and the lab is either 2 weeks ahead of or 2 weeks behind the lecture material. Here we give a mini lecture on the material, and they immediately do the relevant lab, and then we come back and discuss the results. So it's a seamless transition, and the experiments are done in context. Right now we're in a prototype phase. We've done this with 2 sections of 180 students, about 90 in each section. The room holds about 90. We're moving into the large on-term course next term, where we're teaching about 600 students in 6 sections of about 100 each. The staffing cost is about the same as the way we normally teach it. The major cost is the upfront cost of building these new classrooms, and the Institute is invested in one of these classrooms and is building another classroom. Again, it's a flat classroom with 13 tables and a lot of nice space between them. So that's the pedagogy, that's the active involvement with the students. They're much more actively involved than the normal lecture recitation format. We find with this format we get 80% attendance, the students are engaged. In the lecture recitation format you would typically have 50% attendance even with the best lecturer. Unfortunately, there's a tradition at MIT of not going to the lectures in the large freshman courses. So this is trying to reverse that tradition, actually get the students in and engaged in the course material. And this is working. We have 80% attendance, and the assessment shows that the students are actually doing better in terms of conceptual understanding than the normal lecture recitation format. And this is just replicating studies that have been done elsewhere. MIT is not pioneering this by any means, but we are putting it in place here. Let me talk a little bit about the technology, because that's also a big part of it. In particular, electromagnetism is a very abstract subject, and students have a lot of trouble with the concepts because there's not much intuition about electromagnetic phenomena. The way we use technology to overcome that is we have a lot of simulations and visualizations that are built around in virtual spaces, but they mimic the real things that we're doing. For example, one of the experiments we do is measure the magnetic field of a current-carrying coil. And after we do that experiment, we will have a passive visualization that shows the same experimental setup, except we add to that things that students normally can't see. Field lines, for example, or other representations of the field. So that you do the experiment, you see the phenomena, and then you see the visualization that adds things to the phenomena that you normally can't see, that are there but are not seeable. So we're making the unseen seen in the visualizations. We do this in a number of different ways. We have passive visualizations, that is, we make an animation file that shows, for example, when you put the current through the coil, the field getting established, magnetic field, and when you turn the current off, the magnetic field collapses. Again, they've just done that experiment and seen the effects of that on point measurement with a Hall probe. Then they look at the visualization and they see a global characterization of the field, where you can really see spatially all the details of the field animated as you turn the current on and off. That's a passive visualization. That's very important to get an idea of what's really going on. But we also have active visualizations, because there's a lot of research showing that if you're actively engaged in something, that solidifies the learning objectives you want to take home. So in addition to the passive visualizations, we build these using a 3D animation program that's commonly used by game developers and in Hollywood, 3D Studio Max, and we make movies of those. But we also use active visualizations. We have a couple of ways to do active 3D visualizations. These active and interactive ones are not as sophisticated as the things that are passive. That is, we don't have to worry about the length of time for the computation. When we're doing a passive animation, we can spend 8 hours rendering something and then have it go by in 13 seconds. When we're doing something that is interactive, we have to cut down on the detail that we're doing because we can't support that in real time. But nonetheless, there are a lot of things that we can do interactively. Let me just give you an example. We show particles interacting via Coulomb collisions. We show the field lines, and we show them settling down into molecules, for example. That's an interactive program that we have both in Shockwave and in Java 3D, which allows students to build molecules. They can click on a particle and move it around in this 3D space. They can change the properties. They can change the initial conditions. And they can watch to see what happens in terms of their interaction with the environment. Again, these are simpler in terms of the graphics, but nonetheless they're 3D, they're fully 3D, and you can interact with them. They complement the passive visualizations in a very nice way. They allow you to interact with the phenomena you see in the passive visualizations, although they're not as rich in terms of graphic detail. So we have a spread of things like this in terms of technology. And again, the bottom line is to try to help the students visualize things that are very hard to see, to visualize things that we normally describe with very abstract mathematics, and to be able to see them in some gut way in terms of what they look like if you were to represent them in a virtual reality. And I think that's very important, especially with electromagnetism, where it's so non-intuitive and so abstract, and there's so much math floating around. So we have both of these things in the same environment. We have the active learning, the collaborative learning from other students, being actively engaged in the material, actually seeing the phenomena by making measurements of real experiments, and these and using technology to augment the real experiments with virtual add-ons that show you things that are really there, but you can't normally see. But we can construct them virtually so that you can see them. So there's a lot of power in this, and both engagement and both allowing students to get conceptual understanding of things that are very hard to understand in the abstract. It also changes what you can teach. It extends what you can teach, because you can get to concepts which are really quite sophisticated that you would never teach at an introductory level, because the math is too hard. But at least you can reach them qualitatively, because you have a visualization that shows physically what's going on. And you can get to things like the Maxwell stress tensor and energy flow in a much more robust way than you can even in an advanced course in electromagnetism. And you would never touch these things at an introductory level. So it's not only augmenting the material that you're teaching, it also extends the range of what you can teach in these introductory courses. That's what we're doing in physics. Again, this is in a prototype level right now. Next term we're trying to move it into the on-term version of electromagnetism, which up to now has been taught in a lecture recitation format. This is the large version with 600 students. We're also working on a mechanics version of this in the studio format. The goal is, by 2005, to have all of the large lecture courses at MIT in introductory physics taught in this format. We have some smaller courses which are very mathematical for our majors, which would not be taught in this format. But the majority of students would go through this active engagement studio format. There's an obvious question as to whether you can extend this to other large freshman courses. I think math is the most obvious thing that you could would be suitable for adopting to this format. Chemistry and biology. Physics has the advantage that the desktop experiments you can do are relatively straightforward and not dangerous. If you get into chemistry, you worry about toxicity. So there's less range of what you can do experimentally. I do think, however, that the collaborative pedagogy, the interactive pedagogy, really stands on its own. that is you don't necessarily have to do experiments in this format. That the important thing there is engaging the students and having the students work in teams, and collaborate and learn from each other. And I think that interspersed with mini lectures. And I think, my personal opinion is that's a much better way to teach than the large passive lectures that we have now. In terms of cost, to institute this, the upfront cost of building classrooms to accommodate this kind of instruction. We need 2 classrooms that hold 117 students apiece to do this for the large freshman courses, and that's not cheap to build. Once we have those classrooms, the staffing cost has been designed to be the same as what we currently use in freshman physics. So the long-term staffing cost, which of course are the major cost, is approximately the same in both models. So it's really the upfront cost to move to this in terms of classroom space and developing pedagogy and buying desktop experiments. But nonetheless, in any discipline, large lecture course in science at the Institute, I would hope to see, once physics is converted to this format, if it's successful and the students are learning more by objective assessment, that this would spread to other disciplines as well. There's a lot of research, especially in physics and education, that shows that this kind of pedagogy is more effective. This is well established. It's just a question of inertia in terms of moving away from the way that we normally teach to what is clearly a more effective way. And I hope in the future, if we get to 2010, 2020, that this is the preferred way to teach the large courses in MIT rather than the lecture recitation format.